Okay, let's get started. It's our pleasure to have Michael Murdoch, okay, to give us a presentation about his research. And Michael has already been in RIT for 6 years or 7 years? 5 years, okay, 5 years. Okay, and Mike graduated from Cornell in chemical engineering, and later comes to RIT for computer science and for master's degree. And after that, he moved back. He goes to the Netherlands for his PhD in Eindhoven University of Technology and earned a PhD in human-computer interaction. From there, and Michael has already worked quite a lot in LED light and in other color science and in augmented reality. Today he will talk quite a lot in augmented reality here. And recently, I just know he won the NSF Career Award, which is pretty prestigious. And so that is demonstrating a young faculty's research effort. Okay, and yeah. And one small question from me before the starting: what most motivates you from changing from chemical engineering to computer science? Total different major, and are you disappointed from the chemical engineering things, and or you just want to come to RIT to study?
That's okay. We'll start with questions then. So I went from chemical engineering to computer science via Kodak, where I started at Kodak working on film. So when I finished chemical engineering, at the end of chemical engineering, I realized I was very well prepared for a career in like pharmaceuticals or petroleum. And I was like, oh, what have I done, you know? And so I went to work for some of you may have heard of. And it was right at the beginning of the nosedive of film, and I realized that chemical film was going nowhere. And so I got into digital imaging and computer science and eventually HDI and color and stuff. So yeah, good question. It's a good one for academic careers and backgrounds and things. I think mixes are always good. You know, I think it's neat when people change directions. It means maybe it's not the most direct path to where you end up, but it's also following your whims and following opportunities and other things. It's always a good idea. So, good question. Yes, and I did get my master's here at RIT in computer science as a part-timer while I was still working at Kodak. So good times. Anyway, thank you for the introduction. Thank you for having me here today. I was here speaking in this forum about 4 years ago, which was my first year at RIT. Is that add up right? Anyway, and I went back to look at that presentation that I gave there, and I'm actually pleased to say today that I've done a lot of the things that I said then that I was going to do. So hey, that's kind of cool. So I'll be able to tell you a bit about some of those things today. We're talking about color and object appearance in augmented reality. We'll talk a bit about what that means and what I'm interested in that. Please interrupt me with questions while we're going. That's okay with me. I'm not going to try to rush to the end with a lot of slides, and I'd rather have the conversation if it comes up. So please do that. Please feel free. Before I really start, though, I want to acknowledge the students who've been involved with this work. Nargis Hassani is vaguely pictured there at the top, defending her PhD last year. Did a bunch of the early work on this topic. Lili Zhang is pictured below, and she's still currently working on this topic, hoping to graduate next year. Sarah Leary was an imaging science bachelor student who did her senior capstone with me 2 springs ago, and did a great job with that work, and some of that's incorporated here. And currently I have a group visiting graduate students from Hong Kong Polytechnic University working in my lab on this topic now. And one source of a small piece of money for this came from Microsoft in 2016, allowed me to buy a HoloLens and get started with paying students to do some of this work, so appreciate that. So I'm really going to start here. Let you stare at this picture for a minute. I'll tell you about my beautiful trip to Norway. No, not really. I want to start here because, well, what is this? Is this interpretable? This is a photograph of the kind of thing, maybe you've never been to Oslo, but you've seen something like this many times, right? What we're looking at is stuff through a shop window. And what you see is some sort of optical mix of the stuff behind the window, which is the mannequin and the clothing and the stuff on some shelves, and the stuff reflected in the window, which is the buildings and street scene behind me as I'm taking this picture. Strange place to start a conversation about research, but this is actually really crucial to this whole topic of augmented reality, because AR, if I put this headset on my head, which I will just for the style, if I put this on my head, which is the HoloLens, I have a display in here. It's not actually on, but I can see all of you still, right? And this is much different than virtual reality, which would block out the real world and allow you to make some nice virtual content. But this allows me to see all of you still, the whole room, the whole environment, and then add virtual things to the scene. And I can put virtual people here in this room. Who would I choose? I don't know, maybe I would invite Isaac Newton or Einstein or Michael Mann or somebody else who's been involved in, maybe Ivan Sutherland, people who've been involved in the development of AR and stuff. And I can mix them into our very environment, which is pretty cool. But one thing about this is that the display is transparent. And so that's where this optical blend comes in, where if I do put a virtual person in this chair, I will see through them to the chair itself and potentially the people behind and other stuff. And so the overall topic of what I've been looking at is how do we interpret these optical mixes? Because here, you can clear, so there are some places where the mix is pretty strongly biased to foreground or background, right? If you look up here, you pretty clearly see the building in reflection, and there's not much that's high luminance in the background of that, if you want to call it that. So I'll call the foreground the reflection, and the background is the stuff in the shot. On the other hand, this is the opposite, where this mannequin's face is so brightly lit that it pretty much blocks out the bricks and other stuff that's behind it. And there's some intermediates, here where it's sort of medium brightness. You can still see the structure of the building behind, but you can still see the patterns in the shirt on that. So that blend is there. And you can, I think, I assert that you can choose what you're looking at, right? So if you look here, you can choose to look at this, nice red skirt and think, oh, I want to buy one of those. Or you can sort of look through the skirt and see the reflection of these people walking on the sidewalk, right? And you can sort of control what you're paying attention to. And that gives me some feeling, some generation of hypotheses that you can sort of discount the layer that you're not paying attention to. Right? At some point, they're physically mixed, and you can't avoid that, but you're able to discount it. I'll mention that this photograph has fused those two layers in sort of a permanent overlay, right? In alignment. In normal life, you see them move over one another, and that really helps you understand what's foreground and what's background. We look through glass all the time, and we ignore reflections. In part because we kind of have learned what to expect, but in big part because you see how those overlay and cross over one another and change alignment as you move around. So that parallax gives you cue and clues about the depth and the relationships happening here. So anyway, I'll start with that. I also want to give you a little bit of, say, terminology on AR and VR and MR and XR. A few years ago, I thought that we were converging on some pretty consistent terms, but it seems like everybody gives you hard definitions, and my only advice to you is don't believe any hard definitions. It's all a bit fuzzy, and all of this is developing, right? There has been this sort of continuum proposed. I think I mentioned Michael Mann. He was early sort of wearable computer guy. I think he was the one behind this, but this sort of from real reality, which is us here face to face, nothing's fake, kind of in increasingly virtual, increasingly computer generated, up to the virtual reality, which is you block out the real world and you only perceive what's being generated by the computer. In between, there's this idea of mixed reality, where the AR allows you to see the real world and then also add stuff to it. Augmented virtuality, that's a term almost nobody used, but that would be something even more computer generated with only a little bit of real stuff mixed in. And these three lower ones more or less get categorized as extended reality or XR. The middle two kind of get called MR or mixed reality, the idea of augmented reality. Some people are very adamant that AR is only the kind when you're looking through your phone at a scene, so like Pokemon Go style, and I think this is too precise. We haven't yet settled on these definitions yet, so don't let anyone try to convince you otherwise, I don't think. So some examples of what these things can look like, and again, these could be called AR or MR. Now, looking through the phone category is really the most common way people experience AR or MR at this point, right? And maybe you've seen that Pokemon Go example. A couple years ago, that was like the thing, and people, that sort of defined AR, even the other way around. That was the only idea of AR that anyone had ever seen. This example is sort of like an augmented textbook, where with the right app on your phone, looking at some sort of a QR code or something on the textbook, brings some 3D model to view that you can then move your phone around and look at that 3D model as if it were anchored on the desk in real world coordinates, and be able to learn more about it. And maybe it's animated, and maybe it has interaction and other things, which is pretty cool. Another example on the top right would be some sort of augmented driving, where there is a display built into the windscreen of a car or something. That's a picture from BMW. I don't think they really do it like this in actual life, but this is where they're going, right? And to be able to enhance lane markings is a great goal, right? That requires knowing where the viewer's head is if you want to bounce the view off of the screen. Overlaying things like speed or direction things, that's definitely done today, and that's relatively easy. Those stay kind of fixed in your field of view at some distance based on some optics, at the end of your hood or beyond the hood of your car. That's definitely doable today and is reasonably common. Adding these lane marker enhancement or other directionals that are out as if they were in the real scene ahead of you, that stuff I think is coming. It's maybe not fully there yet, but it's on its way. Some other cool examples, this bottom left one would be, maybe that's kind of clear what's happening. I think this is projection based, but like on the torso of a patient in a hospital undergoing some sort of laparoscopic surgery, these doctors have this crazy job of sticking a long probe into someone's body and manipulating it with some tiny camera view on the end of that, overlaying the organs, maybe even real-time imagery of what's going on inside their body. That has there's the idea that could enhance their ability to do their job, right? And the bottom right, that's actually a marketing image from Microsoft. That's one of the things that they use when they're talking about this HoloLens that I had on my head a second ago. If you could imagine sticking the Milky Way kind of in free space above this table and anchoring it there, and the HoloLens has sensors that allows it to know where it is in the space and to know where that table is in the space, so that Milky Way will stay there. And you can walk around and look at it from different directions and spin it and animate it and other things like that. That's a really interesting, being able to add things to your real world for education or for entertainment, lots of things like that. I want to distinguish between two kind of use cases for AR. The top one is kind of what I was just talking about putting a virtual thing into your real space. And again, this is another marketing image, but it's good because it shows you one of the things I was just talking about. The goal here is to put this nice globe on the table, but you can see through the globe to the background behind, right? And there's no way to avoid that bleed through, just like you saw in the shop window, of the background in the foreground. So in this case, you're really interested in the foreground, the AR virtual object, but there's something about the background that's coming through that you kind of like to ignore. And the other one, which I'll get to a little more detail in a minute, is if you are trying to manipulate the appearance or change the characteristics of real-world objects with an AR overlay. And this is maybe, I haven't seen a whole lot of examples of this. This is more like the surgery example a second ago. I'll explain what I'll show you more images of what these cubes are in a minute, but there's a real actual cube there with an AR overlay on it that makes that cube, which is just a piece of styrofoam, look like something different, right? You can make it look like it emits light or like this, or even make it look like it has negative space cut into it just by overlaying graphics onto it. Question?
Yeah, regarding like hardware type of question, the HoloLens, obviously it's futuristic. It's not the most visually appealing thing to put on your face.
Yes.
Because you can't see someone's eye. But like, how far are we from? I know Vuzix, is around here.
Yep.
And like I'm sure all these other companies are working on the same thing. They are. But like, how far are we from having them looking like regular glasses, like kind of.
That's a good question. Two answers. First is, I don't know how far we are really, but the answer is what you kind of acknowledge. Everybody recognizes that that's the goal. Something as light and unobtrusive as eyeglasses is what you'd really want. But you got to fit some sort of projection system in there, and optics and computing power and batteries and all this junk. This Vuzix thing is the closest to eyeglasses looking, but obviously there's a lot of chunky volume there to hold all these parts. These other ones are all different varieties of sort of dorky, ugly gear to put on your face. Convincing people to do that, in an industrial setting, this company is aimed at people who are working on chemical plants and pipes and stuff, and annotating the flow rates on pipes as you work. It's a hard hat environment. What you look like is not really critical, but like going out with your friends with gear like that on your head is a bit weird. And this happened a few years ago with the Google Glass, right? And those people wearing Google Glass got poor reputation and whatever just for having that little thing. And so, yeah, this is a good question. I think everybody wants it to be eyeglasses, even less obtrusive than that. I don't really know how long that will be, but pretty much all the tech companies are working on this, and so it's time, a matter of time, I assume. Yeah.
Will quantum computing come into play with making, I don't know much about, I'm confused by quantum computing or quantum physics, but
Okay.
it's confusing to me. But
I don't know anything about impact of that on this. Cloud computing certainly might have a really big impact, right? If we have a really fast internet connection, it might be better to do your processing somewhere else than on the device that's generating heat next to your head. But yeah. Okay, so I also wanted to point out another distinction here. When you're mixing virtual reality and real reality, you can have the real reality come through a transparent display like this, like I was just showing, or you could mediate it with a camera system, right? So this is actually a VR headset, but it has a camera on the front of it. And you could be using that camera as a live view to blend some portion of the real world with the virtual stuff that you're showing there. And if you do that, you can use alpha matting, compositing, and really occlude the background, right, and layer things properly. This is an example of that also. Looking through your cell phone, you're actually looking through the live view of your camera. So the background here is coming through the camera, and this object is generated in CG in the camera, and those are alpha matted, composited in the graphics pipeline of that system. So these two are both possible with AR. I'm really interested in this one because you also mentioned this idea of seeing people's eyes. You can see someone's eyes through these. It's a little bit like sunglasses, but you can see there. And having the transparent display means the real world is really not distorted in any way, and that's a benefit, I think. It's also better for like seasickness and stuff, that you don't have any temporal lag or anything. You see the real world and the spatial relationships without any distortion, which is good. Yeah, and I flashed this a minute ago just to give you some idea. There's all kinds of companies doing this. I've never seen this one in real life, but I'm really curious if this is like some sort of lightsaber or like digital lipstick device. I don't really know, but if anybody knows, tell me. Right, so finally getting to what I'm researching here. I'm interested in how colors and objects appear in AR, and there's a lot of things that affect this. Here's a list of some. The geometry of what is the geometry of the 3D model that you are putting in virtual part of it, but also the geometry and the complexity of the background that you're overlaying that is interesting. The alignment between those two seems really critical. If you have poorly anchored models that seem to move and shake in the real world, that's not very compelling. Things like color and contrast, I highlighted that bit to say this is where the sort of foreground-background interaction and the blending I was talking about comes into play. This is kind of the focus of my research, and that's why I pull that out. Resolution is a big deal. Also, I didn't mention, but like angle of view and dynamic range, there's a lot of things. And really, to make a good system, you kind of need to solve all of these, because as you know, probably any sort of imaging system, the overall quality is sort of dominated by the worst piece. You could do everything great but have terrible resolution, and it won't be a good system, right? And any of these components could be that piece that makes it not work well. So I've been thinking about perception research in this with AR as sort of a foreground object, and as I mentioned, AR manipulating background objects. And I'm interested in color and contrast, but also the effects of sort of object complexity in both the foreground and the background, and the depth and the mix between them. and this concept of discounting, which is with that picture I started with, the idea that you can focus on one plane and sort of discount the other or ignore it to some extent. This is my cube world diagram of some of these concepts where there's some background. The blue objects here is some real collection of objects or structure. And then on some sort of transparent display, you're creating 3D looking or even stereoscopically 3D objects. And some of them might be like this one, sort of floating in front of the background. And some of them might be aligned with the background as if they were sort of part of the background itself. You know, both of those are interesting to me. So in order to study this, I built this AR setup. It doesn't have a good name. AR setup is what I keep calling it. It's a desktop AR setup. It's a big plywood box. It looks like this on the right. Inside it, essentially, this is what's happening. There is a light booth with some sort of lighting system, a place to put real-world objects, and then you're looking at those through what's a beam splitter, essentially. So you see the light coming from that object directly to your eyes, but you also see the light from a display that's down below, facing upward, bouncing off that beam splitter and into your eyes. And so you see the optical mix created by that half-mirror beam splitter kind of deal. And so what you see over here is the front panel of this thing is off. The display is visible down there, and what's displayed are just two kind of beige cubes, and those two beige cubes end up overlaid with these other printed colors. I'm a color scientist, so I'm always making color targets and patches and whatever else. Right? So here's a sort of printed color background illuminated with real light, but with these two AR patches overlaid on top of it. Hope that's clear. But this basically takes away all the cool stuff of having a head-mounted AR system and puts it in this big box in a lab, but it makes everything controllable, right? So like calibrating a HoloLens is just terrible. You don't want to even want to try. But this means I can control the lighting, I can control the object, I can control the AR, I can control where the observer is looking at it by giving them a people or something else to look at to constrain the perspective or the parallax and other things. So it's sort of the world's most boring AR setup, but it makes it very controllable for the sake of research and experiments. And actually, I had just finished building this when I was here 4 years ago, and I may have even shown this video. Come on, video. You know, 99% of the time, Microsoft makes it all work great. Sometimes it doesn't. Okay, anyway. This video really shows this ghost thing, which is the AR kind of move across it. So this is also the same idea as Pepper's Ghost. Anybody remember from when 1890s or something? The idea of phantasmagoria, I think it was sort of a theater thing. Back before movies, before any of these cool things that we take for granted, having people on stage doing stuff was cool, and magicians and other things, but you could make a ghost appear on stage if you had a big piece of glass and someone, you know, oriented the right direction, and someone off the stage reflected in that glass so the audience would see them as this sort of weird half-transparent mix. And that was a big deal at some point when that was invented. So this is essentially the same idea. It's just in a box on the desk, and I can make the ghost with my computer screen instead of with somebody in costume. So that's kind of cool. You can also look at stuff like this in there. This is an example where the physical background in the box, in this case, is a piece of paper on an easel with white, black, and white. And also this is a physical color target in the box being illuminated with light. These two color targets are in the AR overlay. And I show you this to show you if you have the AR overlay with a black background, there's not much reflected from that background to distort it, so the color checker looks pretty much normal. This one has the light reflected off the background coming through it, and so you see the clear effect of that, right? All the colors are sort of desaturated and brightened by that white light coming through. You can, of course, change the light to whatever color you want. If you change it to red, then you distort it with all these other colors. Interesting to me, this one looks still relatively undistorted because there's not much red light reflecting off that black background. This one is pretty distorted. That one, illuminated with red light, looks, of course, just terrible. It's not at all like red light. So anyway, just to give you some idea of what we can do with this stuff. This is prior art. This is from a paper that really describes the physics well. Usually in color science, you tell people that color requires a light source, an object, and an observer. Yeah? So here we have a light source, we have an object, we have an observer. But here we have something else in between, and this is the AR layer. And this is pretty much like the diagram I was showing you, where there's some light that comes through and gets mixed to the observer's eyes. So this was published, actually 10 years ago now, which is pretty cool. And they also showed this diagram, chromaticity diagram, saying if what color you put on the AR screen is here, it's actually going to get pulled toward the color of the background or the color of the light that's coming through behind. So all of your colors get crushed towards the color of your background in this chromaticity diagram view. They also come higher in luminance. So you're always adding light with this sort of an optical see-through system. So you can never take away light, you can never occlude the background. And so that diagram describes the physics, the sort of accounting for the addition of light. We also have like color appearance models, or CAMs, which account for the effect of surround and luminance levels and try to predict kind of what you would see, how the colors would appear. But neither of those accounts for this sort of cognitive understanding or interpretation of layers and transparency, which again, back to that first photo from Norway, you can somehow, even despite the physics, you can somehow decide which of the foreground or background you want to focus on. So we did a bunch of experiments with overlays on these backgrounds, and this is much like the picture I showed you a minute ago, where these small cubes are AR overlaid on the multicolored background. These are also AR overlays. Now in this case, it's some sort of a spiky object instead of just a flat colored patch. And I think you probably see that this one is relatively undistorted. This one with gray light coming through it ends up kind of lower contrast and a little bit brighter. And with experiments like this, we had people make adjustments to the one on black to match the appearance of that. So if you're looking at this, you're thinking to yourself, okay, well, I just got to make that a bit brighter, maybe a little lower contrast if you have that control, to try to make it match this one. This one over here, you're going to make it a little brighter, probably a little greener, right, to make it match this square over there. And so we had people do these kind of experiments. And I don't want to try to explain all the details on this figure, but this is an A prime, B prime plane, think like C-Lab color dimensions here, where there's a background color, and all of these objects are being pulled towards the background. There's a color appearance model that predicts that the colors should be here to make a match. But in fact, people's matches are out here. And all these little dots are all the individuals. And I leave those there just to show you that there's a fair bit of variation in people's color matches here. But the main effect that I'm interested in here is the fact that people's matches are somehow pulled further away from the background than kind of physics and color appearance models would predict. That's interesting. And that tells me, again, that somehow people are, even though that background is bleeding through and physically there, they're able to discount it. They pull, their matches are actually further from the background than you would expect. So basically fast forward to the end of Narges's PhD thesis. This equation is one of the more interesting findings from her work. And this is in like tristimulus XYZ values, which is physical light essentially. You would expect if you have a background and a foreground and the light coming through them, those would add 1 to 1, right? You add the XYZ to the background and the XYZ to the foreground, and that's what you get. That's what's coming into your visual system. But we seem to interpret that mix as not 1 to 1, but something like 2 to 1, or something a little more than 1 and something a little less than 1, which is interesting, right? Because it's, sorry. Try to do that without making too many noises with my fingers. So this basically, it seems like we make a non-physical mixture of foreground and background when we're interpreting these AR blends, which is pretty interesting. And so we were at first looking at how can we modify the color appearance model to account for this, when in fact, it seems to make more sense to try to account for it almost in light, as if people are doing this calculation in physical light, non-physically, before it even gets to the color grid. So anyway, this probably needs some massaging and reworking as we learn more about this, but this actually does a reasonably good job of describing what we see.
Were people able to move around a little bit? Were you able to tell with the data here whether any of this was the effect of people being able to see it move against the background?
So good question. In this case, these were physically in plane with the background, so there's no parallel. So if you do move your head around, it doesn't actually change where they are. I think if we back the background up so that they're floating in space in front of the background and you could overlay, if you get to the point where the color patch is crossing the boundary to the other background, then I think other things will happen. Yeah, good question. So these were in plane. And so I mentioned in the effect of depth. We're finally getting to that like now. We're setting an experiment with depth differences. Yes.
Yeah, so it's kind of follow up this question. So if it's like object that you try to augment closer or farther, does it affect like I don't know the intensity of luminance, or I mean like if it's closer maybe it's brighter, or so like, and there's also this focal length. Is there any influence on?
I don't think the luminance will change with depth or distance, but the visual size of it might affect something about the saliency. Maybe I think there's more. I'm not sure, but yeah, luminance should be the same. Cool. So I mentioned that this is something like 2 to 1, where the foreground is weighted more than the background in this case. These little alphas seem to also depend on the complexity. So this picture with these things, people discount the background more if you give them a more detailed model than they do with that one, for example. And also luminance here. So the overall luminance of the foreground affects this as well. So there's some more stuff happening, but I think there's sort of this non-physical mixing happening somewhere. All right, so this slide I showed you a second ago, but I want to make the transition from the uppercase to the lowercase here, because I got really fascinated with this idea of manipulating real-world objects. And I had this feeling from sort of computer graphics of texture mapping the real world. So on the right is a cube, styrofoam cube painted gray, with an AR overlay to make it look like a Rubik's Cube. Hey, that's cool. You could imagine this for, I don't know, medicine, for entertainment, for retail, for lots of things to preview things. This is not a new idea. Does anybody know where this comes from, this video? Yes?
Yeah, Disney World,
Yes.
on the Terror, Ride of Terror, I believe.
Haunted Mansion.
Haunted Mansion, I
Yes.
forget the name of it.
Yes.
Yeah, yeah.
So this was from 1950s, 60s, something like that. Projection onto a head-shaped but kind of formless mannequin head model, projecting facial expressions and things that sang with the music and whatever. So that's pretty cool. So basically, augmenting this real-world object with projection is pretty well known, and doing that with an AR overlay that happens to be in a headset. It's kind of the same concept, but a little bit different, right? You may have also seen this kind of manipulation with projection mapping. This is kind of a big deal for light shows and urban fairs and things like that, to be able to project art and video and stuff onto building facades. This is a nice picture because it's showing you how they're really utilizing this sort of rectilinear grid that's part of the architecture and using that in the presentation. It's not like projecting a movie onto the front of a building. That would be kind of like boring. But actually using features of the building as part of your animation, which is pretty cool. So yeah, go ahead.
I know you're more focused on like the color and visual appearance, but I'm curious, like if you go back to the gray cube that you had,
Yeah.
For an image like that, where maybe there's not a huge amount of contrast between the object you want to overlay onto in the background, or maybe the object has like a certain color or lighting or appearance. Have you had any issues with, say, properly overlaying it with like a phone device? I know you have the box set,
Yeah.
but I'm curious if you had any like issues with tracking that sort of situation.
That's a really good question, and I think I will answer it in a couple slides. It's a good segue to my next research question, I think. So yeah, building facades. I have never seen one in real life, but apparently you can get your wedding cake augmented with projection these days. Anything's possible. But an animated wedding cake, it's the same idea, right? It's a white cake, it's got a projector on it, and Cinderella's wagon comes in, and the flowers and the fireworks happen, and whatever else. This is also called spatial augmented reality, so it's in the real world, something's projected onto something like that. So cool. All right, so again, I showed this slide again. I'm interested in this color contrast. You were just asking about alignment, I think, and which is a big deal, and so that's those two come together in this next experiment. So as I mentioned, I have a couple different physically gray cubes, and you can put lots of different kind of overlays on them, right? You can sort of make them brighter, change the shading, change the sort of what the object is, like that. And I got interested in how can you convince someone that you're manipulating the object properties, right? Lightness is a property of an object, right? And it's like how much light does it reflect compared to something white? And usually you can't control that. unless you repaint it. But here I'm giving you a knob that controls an AR overlay that allows you to convince yourself that you're changing the lightness of an object. So I have in that viewing booth now 3 cubes, all lined up, beautiful styrofoam cubes painted by Sarah Leary in 3 shades of gray. You'll note this is the darkest one, kind of a middle one, and the brightest one. And because you can only add light with AR, we were doing overlays on either this one or this one and trying to make them match the middle one. Right? So you imagine you need to add more light to the darker cube to make it match the middle cube, for example. And on the right are some of these overlays. And let me describe what's happening. So this is an overlay that's very tightly fit and well aligned to that cube. And it's also shaded differently. So it's preserving the luminance ratios of the top and the 2 front sides to make it properly shadowed. This is the same shape overlay, but all with 1 shade of gray. So you see that you lower the contrast, and these 2 faces are not sort of physically correct compared to what they would have been. This one is, actually these 2 are both much like that one, except they're a little bigger. So they're oversized for the background, which you could interpret as sort of poorly aligned or over specified or something like that, but they're still kind of the right shape. This one is big and square, so clearly it's not, you have a harder time interpreting that as really related to the background, right? And this is, there's an old idea of veiling luminance, that you can sort of perceive objects behind a veil, and you kind of ignore the veil somehow. You have no problem interpreting the light and shadow or lightness of objects behind a veil if you know that it's a veil. If I show you this one at the top right, you have a hard time telling that it's a veil because it's tightly fit to the shape. If you make it big and square like this, then it's more obvious that it is. And this one with a small square, so basically the whole cube is unaffected except for the small square. That's meant, I included that basically to just relate more like to Nargis's work of patch on patch. And as I mentioned here, we were doing the lightness matching, so I would put an overlay on this cube and ask you to match its lightness or brightness to that cube. And if I show you, for example, this overlay with all the same shade, you're gonna say, whoa, I can't do that because the luminance don't match up. So I really wanted you to focus on the top face. So matching the top face of these 2 cubes, knowing that there's other things happening in the scene and there's surround effects and there's shading differences and contrast differences. You also may notice that there's texture to these, right? There's styrofoam, so there's some bumps here. As you add more light to the foreground, that texture gets lower and lower contrast, which is also something people noticed in the experiment, and it's real life, you know. So this is kind of what the interface looked like, where you're adding something to that, and I give you control over that overlay to try to match it. This is another movie. I don't know if it's going to run either. Looks like today is not movie day. So, but I was just going to show you what it looks like. I had a physical knob that basically adjusts the luminance of that overlay in steps of equal lightness steps. So that was. So you ready for another data plot? These are. You guys good with violin plots or box plots or things like that? I don't know how you like to look at your data, but I've been also playing with ways to illustrate this. Let me just say, the y-axis here is the adjusted L star, so when people dialed in how much light to add, if they nailed this dashed line here, they made a physical match to the center cube's lightness. So here at this X value is this overlay with the physically correct luminance ratios, and this is the distribution of people's dialed in lightnesses to make a match. And what do you know? You get a nice Gaussian tight distribution centered on exactly a physical match. Great, people can make a match. The darker gray side here is for this overlay on the dark cube. The lighter gray side is for this overlay on the lighter gray cube. Both trying to match the same 76-ish L star of the center cube. Again. Sorry, waving my arms too much, I guess. Cool, so these, yes, go ahead.
So they're not actually centered on the dashed line. Is that because you just don't have enough data yet?
They're not centered, huh?
Not, well, certainly the light of the right side of the left violin is below, the mode is definitely below.
Yeah. So mode maybe. I plotted here, I think this is mean and median, by the way, so there's there, you know, and there's some stragglers out there. Let's not complain about this distribution because I've got worse ones for you. Going out here.
Well, I guess if that's the starting point,
Yep.
I was wondering about what to make of the asymmetries.
Yeah, so I mean, like I said, I think I look at that and I say, okay, yeah, people can do a match. You know, standard deviation in here of you know, a unit or two of L-star, that's pretty good, right? Then that's what we.
Meaningless y-axis for me.
Okay, so L-star, like 1 unit of L-star is similar to a JND.
Okay.
Right, so if you're, I think if my standard deviation is similar in size to that, just noticeable difference, then I think that's about at the precision I could expect from the
Sure,
survey.
it's within it, just noticeable.
Yeah, yeah, good point. Cool, so if you look at just the dark gray distributions here, if I go from this physically plausible overlay to the tightly fit but not quite physically right with this single color, there's something happening with the distribution. It gets a little wider, a little biased up. If you make these overlays a little bigger and a little bigger, these distributions get even more ugly and more up, right? The means go up. And then we get to this one with this big, messy, veiling luminance kind of thing. You might even talk me into saying there's something bimodal happening here, but basically the distribution gets much wider. People have much less agreement between themselves and even with their own repetitions. And the mean and median are both much higher. So that means that people are adding more and more light. You're adding more light than you need physically to make the top of this match the top of the center one, because something about this overlay is, the oversizedness of that overlay is making you discount it to some extent. So you have to add an extra light to compensate for that. And again, in units, that's a difference of, whatever that is, something like 8 L-star units. That's quite visible, right? That's not huge, but it's quite visible. You're definitely going to see that difference if they were single patches side by side. But apparently, with the overlay and the geometry here and the surround effects, that's what matches to people. That was looking at the dark gray cubes. The light gray cubes show kind of similar trend, and actually there's some significance calculated here. So you have to go out to here before you start seeing a significant difference between this gray distribution and this gray distribution. And all these other ones are kind of the same. Whereas for the dark gray one, the third one is already significantly different than that, and that trend goes up. I didn't say much about this end one. I have a feeling there's something weird happening there, and I haven't fully gotten my fingers around what this is. This is really like new data from January, and I'm still in the process of extracting what I can from it before I try to publish it somewhere. Question from
Do you think this is, I'm not huge into color science, but I'm familiar with those optical illusions where you've got those grids of colors or like a cube with a shadow, and you think that it's a particular color, but because of the color it's surrounded by, it's actually something else. You're just perceiving it as something maybe lighter or darker. Do you think that's
Yes.
kind of related to this?
I think that is mixed in there, right? And I keep talking about this discounting of foreground and background, but obviously the color of this top face with this kind of bright surround is going to be perceived darker than the physically same luminance here with a dark surround. Yeah. So having a dark surround would make a light object appear even lighter, and the opposite happens there. So that could be part of this, and I should actually go do the color appearance calculation to say what that would predict and see if yet again there's even more difference caused by the AR. I haven't done that yet, but that's a good point.
I'm curious about what the size of these are in visual degrees and about how far apart they are.
I don't remember what the visual degrees were. So in physical size, the cubes are about 4 inches on a side. And so they take up, the three of them together is probably 15 inches wide. And the AR overlay is a 24-inch screen in my box. So it's about this far away from your face. So I can't calculate that off the top of my head, but they're fairly large, right? You're moving your eyes between them to see it. And also, speaking of moving your eyes, I talked to people after the experiment, and when you're trying to match, say, the top face of this to the top face of this, people are looking back and forth here, or sort of like trying to defocus their eyes pointed here and see those two next to each other. And people had a bunch of different tricks that they were trying to do to get this to match.
I have a suggestion and a question for the, so you tried putting the tightly fit on the whole cube, but you're telling people to look at the top, to match the top. Did you try just a top manipulation?
No. I had this one which is all three but plausible, and I had this one which doesn't fill the top. But I did not do that in between, which would be triangle or diamond shape just on the top.
Yeah, I wonder if that would be, the one on the far left, sure looks like that to me sitting back
Yeah,
here.
right.
So I wonder if there'd be a difference. And so the question about your data, how many observations are here, how many people, is this all smushed together? Or?
Yeah, so this is distributions overall people. There were 24 people, and I think I did 7 repeats of everything. So there's a lot of data points for each one of these distributions. Yep.
And have you tried plotting different individuals to see if you've got people's effects making this happen?
Yes and no. There's another interesting effect that over the course of this experiment, people seem to change their criterion a little bit. So people who, so I did it in sort of 4 chunks. You do some on the left, some on the right, some on the left, some on the right. Other people started on the right. And so it seems like regardless of where they start, their first quarter behaves differently than the rest of the experiment. So I actually did this analysis with these significances and the ANOVAs and things. I discarded the first quarter, you get the same results. I discarded the first half, you get the same results. I did, look at the people who started on the left, people who started on the right, you get the same results. So there are some differences, but it doesn't matter to the conclusions of this. And it would be interesting to see, like, one question I've been meaning to answer is this spread due to people disagreeing or people not being consistent within themselves? Because I do have the data to tell that, and I haven't pulled that out yet. Any questions? All right, so to summarize this, as I mentioned, it's kind of preliminary, but the matches that people make in lightness do depend on the reflectance of the cube. The 2 different cubes behave differently. The overlay size or alignment, the cube times the overlay, because there's some interaction effect there, and yes, the observer has some effect too. And yeah, we can look further into that later. And then the overall trend is kind of where this hypothesis started with this concept of veiling luminance, that if you can interpret this as some sort of object in the way of the thing you're manipulating, you would discount it a little bit. And that's, I think, kind of confirmed what we expected, but quantified it in a way on this L-star axis. So I leave you with a couple of pictures, fun things. I'm quite amused that you can create this like negative space and make it look like it's hollow. And by the way, this is the overlay is the same color, same shade of gray in all of these, right? So that the middle cube, which is painted brighter, the mix is more cube than overlay, whereas this one is the other way around because it's a darker cube. So the power of the overlay is higher than the power of the cube behind it. So obviously you can do more with a dark background than you can with a lighter background. But you can make them look like Rubik's cubes and fun things. So to summarize all of this, I've been interested in this idea of foreground background blending and how people discount it. The key to, and at that top line there, this accounting for that discounting in the tristimulus space before you feed it into a color appearance model seems to be the best way to look at it, which is interesting. And on the topic of object manipulation, the alignment really does matter, and it affects your sort of tolerance for how much you can, or I'm looking for the tolerance for how well that needs to be aligned. I'm sure there's a temporal dimension to that, where if an object is moving and your overlay is lagging or somehow jittery compared to that, that's going to make a difference. And in all of those cases, the contrast tends to be limited by the background. Right? You can only add light to the foreground, and you're sort of stuck with whatever light's coming from the background. In terms of ongoing future work, we're currently looking at the effect of complexity and depth in a new experiment that looks like kind of like a blend of these other ones. We do need more foreground-background combinations in order to build a better color appearance model, or to confirm that what we're thinking works. We've also talked a lot about other properties, right? I've been talking about color and color matches and lightness matches, but other properties like opacity or transparency or self-luminosity or texture or other things you can manipulate with AR, even if you're not thinking about color appearance models, you can still mess with these other things. And I'm curious how you do those in a controlled way. Mixed material modeling is another concept from previous work that I'd like to bring in as well. So, thank you for listening.
Do you have any question? Yes.
Can you go back to the negative space?
This one?
Yeah, so what if there was no cube there at all? How much does this image on the left rely on the fact that there is a very dark cube there? Wouldn't I see essentially the same thing if there were no cube there? You're not projecting this on the cube. This isn't the wedding cake, right?
Right.
This is it's being mixed optically?
Yeah. Good question. So yeah, so from lightest to darkest, you're trending toward that black background overlay. That's fine. It's similar, I think, in concept to the wedding cake, where the object, light and shadow, has some effect on what you see. Yes, this was rendered in, I assume it's CG, I just found this image somewhere, to look like it has light and shadow. It's lit in a way that matches the physical setup of these cubes. You could take the cube away and probably convince yourself that there's this fake cube hanging out there. And maybe in that case you've gone too far, right? I'm not sure what to say. Yes, you're right. Yeah, I don't know what to so yeah, if you just wanted a beautiful picture of a cube, you'd be better off looking at it with a black background. Just like with a projector, you're better off projecting it on a white screen with nothing else distorting it. So, but yeah, these different optical mixes, how can you convince somebody that, you know, this texture is really a property of the overlay or not? That's kind of what I'm interested in. And maybe down the line, I would be looking at how would you render this face and the light shadow on it compared to this face in the sort of CG, and knowing how the physical object was
Given what the
illuminated,
background
right?
and the real object was.
Yeah, yeah. So there could be potential mismatch between the computer graphics, geometry, and illumination compared to the real world. Yeah, there's a lot of mixes, a lot of complexity later in this. Good question.
Another question?
Yes.
Still a question about the depth of the object. So if an object, for example, far away, and then you try to overlay some image in that object, so it can be perfectly matched, but this like trajectory can be closer to your eyes, so like this focal length would be different.
Yeah.
Something can be blurred. So how to find this one?
Yeah, so you're asking about some sort of, you know, focal accommodation
Yeah.
versus disparity difference, or matching the physical depth of things. Yeah, I think that's bound to be a problem at some point, right? So right now with these sort of overlays, with optics, the focal plane of what you're looking at is somewhere a couple meters out in space. And so if you are rendering a virtual object at that stereo disparity, then it's fine. But if you're rendering it as if it were way back there, then somehow you get this blur mismatch and stuff. There are people thinking about light field displays and focusable displays. Facebook Reality Labs, Oculus Research, whatever, showed a really wild prototype where there were little servo motors changing the depth, physical depth of the display while they're watching your eyes accommodate, so that so as you scan around the scene and you focus on something that should be further away, it physically moves it further away, magnified by the optics. So people are definitely thinking about that, because if you don't do that, you have the same problem with stereo movies and things, that this vergence accommodation conflict leads to discomfort and people don't like it, whatever. Good question. Yes.
So I just wanted to understand, you said the overlay, it depends on the reflectance of the object itself. And so what if the object is entirely diffused and it doesn't itself reflects a lot of the light? Then how is the optical multiplication going to affect the overall effect of the overlay?
So if I get your question, the brighter sort of, the more light coming off the object itself, the less I can affect it with an overlay.
Yeah, that's my question.
Okay. Yeah.
Is that what you mean when you said that it depends on the reflectance of the object?
Oh, okay. I guess from this conclusion here, I was saying that the actual lightness matches that people make do depend on the cube reflectance. So then I was just saying that, like, the behavior of these dark distributions is different than the behavior of the light distributions. And one of this with dark reflectance and one with a lighter reflectance. So in this, so yes, in general there is an effect, but in this specific experiment, what I was saying was the matches people make were different for the two different cubes at their two different reflectance levels. Cool.
Any other question? So if there is no question, we have a reception outside, and let's thank you to Dr. Michael again and for his wonderful presentation.